Hello, I'm Ryan Crowley.
My name is Chris Long.
I'm Tony Petters.
And I'm Christopher Wheatley Jr., and we wanted to talk to you all today about the effects of cold work and annealing on the microstructure of C26000 cartridge brass.
So, what's the motivation of this experiment? Cartridge brass is a composition of 70% copper and 30% zinc. This alloy is very malleable and has a wide range of uses. Cartridge brass main use is bullet cartridges, and they fail after being fired several times due to the brittleness associated with plastic deformation. It is important to understand the deformation and annealing of the casings to improve a lifetime and performance. Uh, the main reason we want to do this experiment is that most literature on annealing and cold working focuses on the use of different temperatures versus different times, and this lab focuses on the effect of time at a constant temperature.
So just to give an introduction of some of the characterization and testing techniques that were used in this lab to analyze our cartridge brass samples. So conductivity testing was used, and this is a non-destructive test, and it's used mainly to analyze microstructural effects on a conductivity of a material. So the main driving microstructural effect that is looked at is dislocations and grain boundaries. So generally, the process of cold working increases your dislocation density, and these dislocations act as scattering centers for your electrons, making it harder for conduction to occur. So in general, as you increase your percent of cold work, you will also decrease your conductivity. And that's how you can analyze your microstructure with conductivity testing. We also use hardness testing according to ASTM standard E112-10. And this is a non-destructive test that's mostly used to confirm your heat treatment and materials properties. And just for a little bit of theory behind how this works is basically you have something that makes an indent in your material. And if you have a higher dislocation density, there will be repulsions between these dislocations, which will make it harder for that indent to happen. And so your material will give you a higher hardness value. So as you increase the cold work, your hardness will also increase. We also looked at optical microscopy in this experiment. So micrographs can give you pretty qualitative images of your metallic grain structure and allow you to characterize it in, just looking at the size and different other properties and other defects. But you can also perform grain counting to get a quantitative analysis and quantitative data. This can be performed according to ASTM standard E1004. And the main value that's looked at is your anisotropy index, which is the degree of anisotropy or how much your material is different in two different directions. So the equation can be seen to the right here, and it is the average grain length in a 0-degree direction divided by the average grain length in a direction perpendicular. And in this experiment, our 0-degree direction was the rolling direction for our cartridge brass samples.
So based on all that information, we have 5 main hypotheses that we want to test here. The first one is that as cold rolling increases, our hardness will increase and conductivity will decrease. This is more, again, to confirm what we kind of saw on the information slide. And we also want to check and see how much that's going to change based on cold working. Our second hypothesis is that increasing the cold rolling reduction will decrease the average grain size and alter the grains to become more oriented and anisotropic. Our third hypothesis is that annealing temperature should return macroscopic properties and brass microstructure to their pre-cold work conditions because annealing creates a recrystallization process that allows new grains to form and create a new structure. Annealing should also induce that recovery, recrystallization, and grain growth with this new equiax grains relatively free from stress. This would counteract the anisotropy index that we see as a result of cold rolling. And our fifth hypothesis is that materials with a higher degree of cold rolling should react sooner to the annealing process. This is because we're putting more energy into the system in the first place based on the amount of cold working we're doing. And so if this recrystallization happens at a given energy level, it would be easier and faster to reach that level if you have a higher amount of energy in the system in the first place.
So the procedures on how we carry this out, like Ryan said, we have 17% copper, 30% zinc cartridge brass that we used. All of our 10 samples were pre-annealed to kind of normalize the microstructure to the same way. And then they were cut into different sections and cold rolled at 0, 20, 40%, and 60% reduction in the thickness of the strip. And all of them were annealed at 450 degrees C for varying times for as little as 1 minute and for as long as 1 hour. For the testing of this microstructure, we performed hardness testing on a multi-tutorial hardness tester on the Rockwell B, F, and G scales, depending on the softness or hardness of the material. And we did at least 6 measurements for every sample. To compare all of these, we converted them to the Vickers hardness scale so we could see how all of them compared. And for conductivity testing, we used an Ether NDE Sigma check to eddy current meter, which measured percent IACS and liftoff, where we did 5 measurements of each sample. Finally, for the optical microscopy, they were all ground with silicon carbide paper and polished with 1 micron and 0.1 micron slurry. And then they were viewed in several different regions and at various magnifications to get that qualitative and quantitative analysis that Chris was talking about.
This is a table of our annealing times and the percent cold work. Initially, all cold works were annealed at 0, 5, 10, 30, and 60 minutes. But looking at our experimental results, we're finding that some percent cold works, we can neither confirm or deny our hypothesis. So we had to go back and do new annealing times to get that data. All the annealing times and percent cold work are indicated by the highlighted X's. So here are some results for the percent cold work. This is a micrograph of the 0-minute annealing time at 0, 20, 40, and 60% cold work. From these micrographs, we found that increasing the percent cold work increases the dislocation density. You can see that it also increased the anisotropy along the axis of cold rolling. And we can also see some slip planes in the 20%, 60, and 40% percent cold works.
Now, looking at the recrystallization, we looked at the 60% rolling reduction for kind of the most drastic and easy to observe grain changes in grain size. So from A to C, you kind of see the first process of recrystallization where at 1 minute, you have tiny dots all throughout the grains. Those are baby grains that are starting to be recrystallized. In part C, you can see that it's almost all entirely baby grains with only a few of those elongated grains from cold working. And from D, the new grains have basically taken over. Basically, all of these are free from stress as we had hypothesized. And then from D through F, you have the process of grain growth where these new stress-free grains are growing in size towards that grain size that we originally saw with our uncold work sample. So you can see this change in anisotropy visually. We were also interested in seeing how much that these grains had recovered back to our original samples. So in A, you have our uncold work sample that is just completely annealed, and that's kind of our baseline for how much these grains can recover back to their original position. And you can see with increased degrees of cold work, 20%, 40% to 60%, there's a general trend that with each increased cold reduction, the grain sizes are ultimately smaller. So all of these are at 60 minutes, 1 hour, our maximum annealing time, just to see at these longer times, how far of recrystallization process can we get. And so you can see that none of these actually achieve the same grain sizes as our original brass sample. And so this tells us that the recrystallization process is not necessarily complete, or the grain growth process is not necessarily complete. So there's some recovery, but not a complete one.
Looking at some of our quantitative data, the values for hardness for each cold work at various annealing times can be seen on this slide. And just first looking at the vertical axis where we have 0 annealing, we can see that the hardness increases as you increase the percent cold work. This makes sense based on what Ryan was talking about seeing a higher dislocation density. And one interesting thing to note about each of these trends is they follow the same trend of a slight increase followed by a sharp decrease in a plateau. And the interesting thing is that as you increase the cold work, the time that it takes to reach that plateaued value decreases. So this relates to the hypothesis that Tony was talking about, that perhaps because these higher cold work samples have a higher internal strain energy, they require less thermal energy to begin the process of recrystallization and recovery. And finally, from this data, we can also see that our hardness values after annealing are still higher for all of our cold work samples. They're higher than our uncold work sample. And this is related to what Christopher talked about on the last slide with the grain size. And it really lends some support to the fact that there is a partial recovery, but not complete, because our properties did not return to their expected value.
Moving on to our conductivity values here, we can see annealing time versus conductivity in percent IACS. And as you look at the zero amount of time annealed, you can see that the 60% cold work is the lowest conductivity. That's, again, that makes sense considering especially what Ryan said and what Chris talked about just before me, is that this dislocation density causes a lot of problems because that's a lot of interference with electrons when they try to move through the sample. You do see here that most of the values do recover to what the unannealed samples were. You see them recover to their natural state, but you also see towards the end, towards the later conductivity annealing times, you see that some of the conductivity values increase. This could be a result of an error in the machine, or like just experimental issue in some other way, but it could also be something to do with the structure itself, whether or not the dislocations have aligned themselves in a way that allows electrons to move, or if there's like a solid solution where copper and zinc kind of split apart a little bit, that gives a location where electrons flow more freely. This information, while it does revert to our original numbers, it does raise some questions as to why they're higher. We would expect them to be lower.
And finally, looking at the results for our anisotropy index, again, looking at our 0 annealing time samples, you can see that the anisotropy index really greatly increases as you increase your percent cold work. This makes sense, again, calling back to the micrographs that Ryan showed us with the very long and thin grains. If you look at the equation again for anisotropy index, it's length in the rolling direction divided by length in a perpendicular direction. So as they get very long and skinny, your anisotropy index, of course, is going to get very large. And we can see from this data that all of our values returned to the original value of about 1, which would indicate circular grains. They return to that value after about 5 to 15 minutes. This makes sense, and it shows that recrystallization did happen because it creates strain-free equiaxed grains. And similar to our hardness data, we can actually see that higher cold work percentages, their anisotropy index returned to a value of 1 at much lower times than our other cold work samples. So this, again, just relates to the internal strain energy that they possess, and they require less thermal energy to return back to some of those original properties.
So our experiment wasn't without issues. First off, the furnace that we used is a door furnace. And so that means in order to insert and remove samples, you have to open a door. And when you do, that releases a lot of the energy that is inside as heat. It releases that out to the atmosphere, which increases the outside temperature and decreases the furnace temperature. This is important at lower annealing times, because if samples are only in for like 1 to 2 minutes, the furnace isn't even. It's not going to have a constant temperature of 450 degrees Celsius necessarily. It's going to be building back up to that 450 degrees Celsius temperature. This can cause an uneven annealing process, which can alter the data profoundly if you aren't able to give it enough time. This isn't as big a problem if you go to like 30 or 60 minutes, because the furnace has enough time to get up to temperature and allow that recrystallization process to begin, because it has that constant temperature for most of the process. It is also hard to measure the energy released from these samples, which means it makes it hard to understand just exactly when it begins to recrystallize. We have a thermodynamic definition where like recrystallization begins at X amount of time and X percentage, but we want to, it's difficult for us to make that call right here, right now, because the energy we have is so varied based on what the furnace did and how much heat it lost before gaining it back after we close the door.
So looking at our conclusions, it was supported in our hypothesis that increasing the amount of cold work would decrease the conductivity while increasing the hardness. And it was also supported in our hypothesis that when we annealed the brass, it could revert the material to a pre-cold work state. And the microstructure and hardness supported a partial recrystallization, that we didn't completely reach that pre-cold work state, but we almost got there. And with the hardness values themselves, none of the cold work samples reached that original value, which supports partial recrystallization. However, with conductivity, it was found to be completely reverted back to its original value, with even some of them being at a higher conductivity than our original value, which sets forward all sorts of interesting ideas on what could be going on with the conductivity, whether it's just an error in the conductivity meter or something going on with the microstructure itself. And then finally, as we saw, that we did see a return of new stress-free equiax grains that we would expect from the annealing process. But as you look at our references, I want to thank you all for listening to our presentation, and enjoy the rest of your semester and have a great break.
Thank you very much.
Thank you.
Thank you.
Solid.